Bonjour tout le monde. This video we're going to be talking about correlation. Again, we already took a look at correlation back at the end of week 3. After all, defining it both as a way to measure how closely two variables are to having a linear relationship, and as a useful alternative measurement to covariance. While both of those things are true though, there's far more to correlation than just that. Correlation is our gateway to the concept of linear regression, an idea so fundamental to how we practice statistics that it's going to take us 2 whole weeks worth of work to explore. This video then can be thought of as the prelude to that exploration of linear regression, with correlation being the bridge between the first half of the theory for this module and the second half. Our first learning objective for the video will be to reconsider correlation in greater depth, including looking at the most common method for defining correlation, which is Bravais coefficient. Our second learning objective is to study a hypothesis test based on Bravais coefficient, which helps us determine whether we can be sure that the correlation we are seeing in a sample exists at all. Our third and final learning objective will be to consider 2 alternative methods for calculating a value for correlation. Before we go any further, we need to consider the standard warning about correlation. It is not the same thing as causation. The fact 2 random variables exhibit some kind of linear relationship, possibly even a very strong one, does not in itself mean that changes in either variable cause the changes in the other variable. All sorts of other things might be happening. Let's consider an example of this. There are several online stats that claim ice cream sales are strongly correlated with shark attacks. Now, I haven't been able to find the data that these sites are using to make this claim, but it doesn't seem like it's an unreasonable possibility. Now, that isn't because I think eating ice cream makes one more susceptible to shark attacks on beaches. And it isn't because I think that after you've watched somebody get attacked by a shark, you might suddenly be in the mood for an ice cream. It's because I can see why both ice cream sales and shark attacks would increase with temperature. If we weren't measuring temperature though, and instead we were just looking at how shark attack numbers change along with ice cream sales, we would miss the fact that both are being driven by changes in a third variable. This is an example of what we call confounding, in which a variable we haven't considered is driving changes in the other 2 variables, which therefore leads to them being correlated. Sometimes there isn't even a confounder, as the website tylervingen.com shows so well with its spurious correlation graphs. Sometimes we're just dealing with sheer random chance. Generate enough scatter diagrams using enough data sets, and sooner or later you will find completely unrelated variables that just so happen to be well correlated, at least for the data you have. It's very hard to believe, for example, that there is any confounder which drives both margarine consumption and divorce rates in the US state of Maine during the noughties. Though if you can think of any confounding variable that might be in effect here, I would love to hear what you think that is. It's a common complaint among statisticians that no matter how many times we remind people that correlation does not imply causation, there are always people who insist that it does. I actually think we may have generated the opposite problem these days. We've spent so much time spreading the message and doing it so effectively that causation and correlation are not the same, that people will insist correlation doesn't imply causation, even in situations where causation has been determined, and we're just using correlation to measure the strength of that causal relationship. Either way, though, we need to make sure that we as statisticians are properly judging the evidence. Fundamental to the study of correlation is the scatter diagram, or scatter plot. As a reminder, scatter diagrams allow us to visually represent paired data values. We think of these paired data values as being realizations from 2 random variables. We plot the realizations from one variable along the horizontal axis, and we plot the realizations from the other variable along the vertical axis. As we saw in week 3's video on covariance and correlation, the correlation is a measure of how close the points in a scatter graph are to lying on a straight line. Positive correlations mean the points are clustered around a line with a positive gradient, with wider clusters corresponding to smaller positive correlations. By the time the correlation gets very close to zero, it is hard to visualize whether the line should even be going up or down, or where it should be in general. Similar rules apply when the points are clustered around a line with a negative gradient, but in this case the correlation is also negative. Now, you've seen these pictures before, of course. Here's the new part. Each of the correlations I showed you on the previous slides were Bravais correlation coefficients. The formula for the Bravais correlation coefficient for n data points is now up on screen. It's another one of those formulae that looks very unpleasant, but it is also another one of those formulae that R is going to handle for us anyway. An extremely important point that needs to be made here is that, while Bravais came up with the formula I am showing here, the statistical literature very commonly refers to this as Pearson's correlation coefficient after the mathematician who popularised its use. I will not be using that name in the videos or in the course more generally because of Pearson's foundational role in the pseudoscience of eugenics in Britain, and because of his documented history of racist and anti-Semitic beliefs and statements. I feel it is my responsibility as an educator to let you know of the common name for this coefficient in order to avoid your confusion. But I also feel it is my responsibility as an educator to not perpetuate the practice of name-checking truly appalling people when we do not have to. The Bravais correlation coefficient is tremendously useful in summarising linear relationships. There is a problem, though, lying in that use of the word linear. There are many relationships two values might have that are not linear. The Bravais correlation coefficient will often completely fail to pick up on those relationships, even if they're very strong, because it's not what the Bravais correlation coefficient is designed to do. The curved relationships we're seeing on screen now, for instance, are clearly very strong, but the correlation values are extremely close to zero, because if it isn't a linear relationship, the Bravais correlation coefficient doesn't care. One final very important point about correlation is that it is invariant under linear transformation. Now, that's a big and horrible phrase, but it translates into plain English very simply. If we linearly transform x, the correlation doesn't change. If we linearly transform y, the correlation doesn't change. If we linearly transform x and y, the correlation doesn't change. Now, this is extremely important because there's many situations in which it is helpful to linearly transform variables. We've seen already the ways in which transforming random variables so they have a mean of 0 and a standard deviation of 1 is useful for creating z-scores and estimating probabilities, for instance. And we will see another application of this in week 8. It's extremely useful to know that we can perform these transformations without having to worry about whether the correlation has changed as well. To give an example of this, let's return to the car's stopping data. If we transform the stopping distance from feet to inches, we see no change in the correlation value. If we also change the speed from miles per hour to kilometers per hour above 30, which means some values will become negative, we again see no change in correlation value. These three pictures show very well why the correlation doesn't change. We are getting precisely the same three graphs, just with different axes. The correlation between two random variables is a parameter. That means there exists some true value of the correlation, which we will usually denote using the Greek letter rho. Just as with any other parameter, we generally have no hope of ever knowing what the value of rho is. All we can do is estimate it for our data using a statistical value, usually denoted little r. In particular, when two random variables are independent, their correlation will be 0. Their true correlation will be 0. However, it is almost impossible for the value of r we calculate from data to be 0. Try rolling pairs of dice and calculating the correlation of the values you get on the dice, for example. Even though the dice rolls are independent, the value of r you calculate will not be 0, though it could be very close. Different samples of pairs of values from x and y will generally give us different values for r. This means r, just like x bar, p hat and so on, has a sampling distribution. This also means that we can perform hypothesis tests on our value of r. The idea here is to define the null hypothesis as ρ equals 0. That is, there is no actual correlation at all. We then consider how far from 0 the sample correlation is, and from that decide whether it is so far from 0 that we can reject the null hypothesis that ρ is 0. The advantage of this approach is that if we can reject the null hypothesis, we can at least be sure we have the direction of the correlation correct. Now, doing this in the general case can be somewhat tricky, so we're once again going to reach for one of our favourite assumptions, and we're going to assume normality. Formally, our two assumptions for a hypothesis test for ρ are 1. The paired data values little x and little y we are testing come from a random sample, and 2. The random variables capital X and capital Y for which our paired data values are realizations are both normally distributed. Remember, if we want to check whether realizations are coming from a normal distribution, we can use QQ plots or the Shapiro-Wilk test to investigate. So let's go through the steps for a hypothesis test for ρ. Our null hypothesis, as mentioned, is that ρ is equal to 0, and that is what we would have if x and y were independent. We once again have three options for our alternative hypothesis: left-tailed, right-tailed, and two-tailed. And we choose one of these depending on whether we're most interested in whether ρ is negative, positive, or simply non-zero, respectively. For any of these tests, the test statistic capital T is equal to r multiplied by the square root of n minus 2 divided by the square root of 1 minus r squared. I'm not going to go through the theory as to why this is true, but the formula is now up on screen. The distribution from which we take a critical value for this form of test is once again the t distribution, this time with n minus 2 degrees of freedom. Once we have the test statistic capital T and a critical value, or once we generate a p-value by finding the probability of getting the value of the test statistic, or a more extreme value from the t distribution, we continue in the same manner as usual. We either reject the null hypothesis that ρ is 0, or we fail to reject it. Now, this is a good opportunity to remind everybody that demonstrating a result is statistically significant is not the same as demonstrating that the result is at all useful. If you have enough data points, we can demonstrate even extremely weak correlations are definitely positive or definitely negative. Under what circumstances, though, is it worth proving that ρ is definitely positive in a situation in which r is equal to, say, 0.02? The Bravais approach to correlation has a lot to recommend it. There's a reason we teach it first. It does have its limitations, though. We've already covered the big one. If either x or y aren't normally distributed, we can't use the Bravais correlation coefficient to construct a hypothesis test for ρ and expect it to be very good. We've talked before about how assumptions of normality can often be robust, but they can be broken badly enough to start causing a problem. One obvious case of this would be if either x or y, or both of them, are ordinal random variables. There are many situations in which knowing how closely an increase in a continuous variable links to a change up or down in ordinal categories can be useful, and so we need to consider how we can do that. A good way to do this is via the ρ correlation coefficient. This, as with the tests we considered at the end of week 4, is a non-parametric approach. As a reminder, this means that we make no assumptions about the underlying distributions, and hence the forms of parameter, that are generating our realizations. I will note at this point that the ρ correlation coefficient was first used by Charles Spearman, and Spearman, whilst not as outwardly and gleefully racist as Pearson was, also spent a lot of time attempting to find scientific justifications for racist assumptions, and so I will not be using his name going forwards either. Again, like the non-parametric tests we've already looked at, the row method works by assigning rankings. We arrange the x values in ascending numerical order, and we give each value a corresponding rank. We then do the same for the y values. We then calculate the Bravais correlation coefficient not for the data values themselves, but for these paired rankings. Let's quickly do an example so I can show you what I mean. Here are the 2023 stats for Jamaican sprinter Elaine Thompson-Herah's 100-metre races. I have the time in seconds and the corresponding placements. Since placement is ordinal, we cannot use the Bravais approach here. We next rank x and y. Where we have ties in data, as we do here, we give each tied value the average of the ranks. Here first takes a first rank, third takes a second rank, and fifth takes the third rank. Therefore, for this setup, a positive correlation in this context would tell us longer times for a run correspond to finishing the race behind more other runners. The row coefficient for the data is equal to the Bravais correlation for the rankings of the data, which in this case is negative 0.23. This suggests a weak negative correlation. There is a slight tendency for running slower to mean placing better in a race. Now, this is counterintuitive, of course. One possible explanation for this is that there are many variables which we are not taking into account. Weather conditions, who else was running in those races, etc. Really though, the much better explanation is just that because we have an extremely small sample size, we shouldn't be drawing any conclusions from it at all. How does this approach help us with hypothesis tests? Well, I won't fully go into this, but I will briefly explain. We can take each pair of ranks and find how many of them have the second rank higher than the first. We will call that number lowercase m. Under a null hypothesis of no correlation, we should get this arrangement roughly half the time. We can then use a binomial distribution with lowercase n trials, so that's the number of data points, and a probability of success 0.5 to see how likely we are to see a value of lowercase m, or a value even further from n over 2. The row correlation coefficient is an extremely flexible approach. It works for ordinal data, nonlinear relationships, linear relationships involving non-normal values, and linear relationships with normal values. So it works quite well even in situations where the Bravais correlation coefficient is appropriate. So why don't we just use it every time? Well, there's two reasons. One is that the hypothesis test for the Bravais coefficient is superior to the hypothesis test for the row coefficient, assuming that the assumptions for the Bravais coefficient actually hold. The second reason is that very often we want to be able to use the data we have to make predictions about what future data might look like. The Bravais coefficient makes up part of a method that allows us to do that, as we shall see, whereas the row coefficient does not, or at least not to the same extent. I'm going to show you one final method for finding a correlation coefficient, and then we'll wrap up. Kendall's tau correlation coefficient is another non-parametric approach to calculating a measurement of correlation. This has some similarity to how we consider hypothesis tests for the row coefficient. We first label each data point with a value between 1 and lowercase n. We then compare each single data point, lowercase x subscript I, lowercase y subscript I, against every other data point, lowercase x subscript j, lowercase y subscript j, where j is greater than I. And we make that last point just to make sure we don't end up comparing every pair of points twice. The way we perform a comparison between 2 points is as follows. A pair of points is called concordant if the sign of lowercase x subscript I minus lowercase x subscript j is the same as the sign of lowercase y subscript I minus lowercase y subscript j. A pair is called discordant otherwise. In other words, we have concordance if the direction of change between the x values is the same as the direction of change in the y values, and we have discordance if the direction of change between the x values is opposite to the direction of change between the y values. We then find the value tau using the equation on screen. Note that the number of comparisons we will need to make will be n times n minus 1 over 2, so the value of tau will be 1 when every pair is concordant, and -1 when every pair is discordant. Right, summary time, innit? Correlation is not causation, though correlation can be very useful when considering how causation is working. Correlation is a very good way to summarize the linear relationships between two random variables, but we have to recognize that many relationships are not linear. Finally, there are multiple different approaches we can take to calculating a correlation variable with different tools, different approaches having different advantages in different contexts. In our next video, we'll take our first step into predicting the value of one variable from the value of another variable, or even from multiple other variables. We'll start by looking at the idea of the line of best fit. How can we draw the best line of best fit, and how do we declare best in the first place? This approach is known as linear regression, and as we shall see next time, our starting point for this topic is closely linked with the concept of correlation. A bientôt. Konnichiwa. In our last video, we talked about various ways we can measure correlation, which itself measures how close two variables are to having a perfect linear relationship. One of the ideas we covered that there are various ways functions can describe the relationship between two random variables. So why are we so focused on straight lines? The answer to that question is going to take us 2 weeks to fully consider, but we're going to make a start in this video. Using straight lines allows us to make use of a technique known as linear regression, which is an extremely powerful and commonly used type of regression method. This, though, just raises the question immediately of what I mean by regression in the first place. Our first learning objective for this video, then, is to go through the concept of what regression actually is. The short version is that it's a process by which we input values we have to get a prediction for a value we don't have. But there's a lot more to be said on the topic. Our second learning objective is to consider those ideas that specifically describe linear regression. One important aspect to linear regression is the idea that there exists some kind of true linear relationship between two random variables, and that what we are doing as statisticians is trying to approximate what that linear relationship is. Seeing how to do that most effectively will be our third and final learning objective for the video. Let's start off with an example of a situation we might want to use regression for. Let's say you want to buy a used bike to cycle around Durham. Now, there's lots of possible bikes you could buy through various shops or websites, and you want to make sure you get a fair price for the bike you buy. How can you come up with an estimated price for a used bike? Well, you'd want to take into account various different pieces of information. How old the bike is, what the make of the bike is, how many gears it has, the number of previous owners perhaps, and so on. So what would be really helpful would be if you could take those values, plug them into some kind of formula, and get out an estimate for a fair price for that kind of bike that you could then compare with the actual prices being offered to see what is and isn't reasonable. Now, this fundamentally is regression, using values we have to predict a numerical value that we don't have. Let's break down how this works in general. We are going to need one or more inputs. We call the variables we take values from to get inputs the predictor variables. In our used bike example, the predictor variables are age, make, gear number, and the number of previous owners. We think of each of these predictor variables as being a random variable. We will see later that it's important these predictor variables are independent of each other, or at least we can pretend they're independent of each other without too much trouble. For this reason, the predictor variables are also called independent variables. Generally, we label these values with capital X subscript 1 through to capital X subscript P, and we will come back to this, the meaning of this term p later. The value we are trying to predict is also a realization of a variable, what we call the response variable, because it takes a value in response to the value of the predicted variables. We commonly label this variable capital Y. We also call this variable the dependent variable, to contrast with the independent variables. The idea here is that the response variable is literally dependent upon the values of the independent variables, which we hope are independent of each other. In this module, we will assume that there can be multiple independent variables, but only one dependent variable. Now that latter condition can be relaxed, but we are not going to here. So we have a list of inputs, age, number of previous owners, etc. And we put these into a regression function to get a value for an output, in this case price. Now the key word in what I just said was function. For regression to work, we need to know what kind of function we're going to use to turn inputs into outputs. One option for our function is for it to be linear, and this is where linear regression comes in. We're going to start talking about linear regression with a specific case, what we call simple linear regression. Now, whether you end up thinking this approach actually is simple is not for me to say. The reason the approach we're about to look at is labelled as simple is because it uses just a single input. So it is the most simple situation we can apply regression to. In fact, this is a situation you may very well have seen at school, though with a lot less formal language attached. Did you ever do an experiment in your class to compare, say, height against foot length? I remember doing this when I was a child. We measured the height and foot length of each pupil in the class and then displayed the results on a scatter diagram. Now this had two purposes. First, it showed there's a relationship between height and foot length. And second, it showed that the relationship looks at least sort of like a straight line. Secondly, we could then use this straight line in order to make estimations. Now this is literally all simple linear regression is. Get your data, draw your scatter diagram, draw your line, and make estimations if you want to. There are some theoretical ideas linked to this which we'll consider later in the video, which is where things get trickier. But my point is, the process of performing linear regression isn't at all unfamiliar to you in terms of what it does. So why is this material that I'm teaching at university rather than in a secondary school? Well, when we introduce this idea to school children, we generally tell them to draw the line that looks right, that looks like it's best. Now this could lead to more than one line being drawn, none of which look obviously wrong, and that in turn means we can get different estimates being given by different lines for the same input. If we look at the cars data in R, for instance, and try to draw a line expressing the relationship between speed and stopping distance, there are a number of plausible lines which we could draw. It's clear each of these lines captures something close to a relationship that generally seems to exist. So which of these lines should we use? Simple linear regression allows us to answer that question, drawing a line for us that is, by some measure, the best. So how do we draw what we might call the best line of best fit? Now I'll answer that in a few minutes, but first we need a little bit more notation. You should already be aware of how we write an equation for a straight line, but here is a reminder. Commonly, we use the equation as on screen, using m to represent the gradient or steepness of the line, and c to represent the y-intercept, the value y takes when the line passes through the vertical axis. Now we're going to use the same equation, but with different terms. Let's go through the changes from the previous equation to this one. The nice easy bit is that I've relabeled the gradient and the y-intercept. Now instead of m and c, we have lowercase b subscript 1 and lowercase b subscript 0 respectively. We'll return to the meaning of those subscripts later, but for now, just please accept that this is the notation we're going to use. Perhaps the biggest change here is that we're using y hat instead of y. We do this to make it clear that the regression line will be used to find estimated values of y, We've used the hat notation before in week 4 to represent finding an estimate, and here we do so again. The other new notation we're going to use involves how we label data points. We will assume that we have lowercase n data points in our scatter diagram, and we will label the points lowercase x subscript 1, lowercase y subscript 1, and lowercase x subscript 2, lowercase y subscript 2, and so on, all the way up to lowercase x subscript n, lowercase y subscript n. Now, it doesn't really matter which point we give each number to, as long as we don't swap those numbers around once they're assigned, as long as we're consistent. The lowercase y values, lowercase y subscript 1 to lowercase y subscript n, are the true y values. So these are the data values we've actually collected. For each value lowercase x subscript I, we also have a value lowercase y subscript I hat, which is the value, the regression line it gives us as the estimate for lowercase y subscript I. Right, we are ready to talk about finding the regression line. Finding this line uses something we refer to as the least squares criterion, a fancy name that breaks down into what I hope you'll think of as a simple idea. We'll start with the fact that when we draw our line, the line isn't going to go through every point, not unless the correlation is 1 or -1 at least. And in those circumstances, we don't need to use regression, we already have a perfect linear relationship. That means we get differences between the values of lowercase y, which are the true data values, and the values of lowercase y hat, which are the values the line gives us as estimates. We can think of these errors as how well our model is working, or we can think of the size of these errors as giving us a sense of how well our model is working. We denote the error for point I as lowercase e subscript I, lowercase e for error, and we define it as equaling lowercase y subscript I minus lowercase y subscript I hat. Therefore, the positive error e subscript I tells us that we have underestimated y subscript I, and a negative error means we have overestimated y subscript I. Now, we would like these errors to be as small as possible overall to get a sense that our model is doing well. But what does as small as possible overall actually mean? How do we find it? Well, we could try adding all of the values of e subscript I together to see how big that value is. The problem is that an e subscript I value will be positive each time a point lies above the line and negative each time a point lies below the line. These positive and negative values would then at least partially cancel each other out when you add them all together. Now, a fix for this is very simple. Rather than adding together each of the e subscript I values, we add together the values of all the squared e subscript I values. Squaring makes every one of these values non-negative, so we no longer need to worry about values working to cancel each other out when you add them together. We are therefore adding together a sequence of square numbers and looking for the line that gives us the smallest value in doing so. This is why we refer to this as the least squares criterion. And that's it. That's genuinely it in terms of what a regression line is. It is the line which gives us the minimum possible value for this sum of squared e subscript I values. Job done. Well, not quite, of course. The question now becomes how we actually find the line which gives us this minimum value. The formula for the line of best fit is now on screen. Note the use of the sample means of x and y here. I'm not going to go through why the equation has the form it does, though we'll be coming back to this expression later. What matters most from our perspective for now is that R can find this line for us with a single line of code, as you'll see in this week's workshop. We refer to the equation giving us the regression line, rather unimaginatively, as the regression equation. Let's go back to the cast data. By use of the LM function in R, I can calculate the regression line for the scatter diagram as the regression equation y hat equals 3.932 times x minus 17.579. Now, as we can see, this is a pretty good line in terms of approximating the relationship between how fast a car is going and how long it will take to brake. Using the line to generate estimates is nice and simple. A car going at 50 miles per hour, for instance, has its stopping distance estimated at 41.4 feet. One particularly nice feature of a regression line is that it always goes through the point x bar y bar. That means our prediction for the sample mean value of x is always the sample mean value of y. And there you go. Get your data, use R to generate the regression line, use that line to make predictions, bosh. That's it for this video in terms of the calculation and use of a regression line. What we still need to consider, though, is the theory that tells us that any of this is actually reasonable. Let's go back to one of the fundamental ideas in the approach to statistics that I've outlined. Our job is very often to use statistical values to find estimates of parameter values. We assume true values for those parameters exist, but we'll never be able to actually find them. Instead, we use sample values, so we use the sample mean as an estimate for the population mean, for instance. Now, we're actually doing a very similar thing here. We've made the assumption that there is a linear relationship between x and y, an actual slope and y-intercept that truly represents this relationship between the variables. The problem is, just as always, we can't actually find those values, we can only approximate them using statistics. In other words, those true values of the slope and the y-intercept are parameters. We use beta subscript 1 to denote the true slope parameter and beta subscript 0 to denote the true y-intercept parameter. What we call b subscript 1 then is an estimator for beta subscript 1, and b subscript 0 is an estimator for beta subscript 0. These values b1 and b2 are both statistics. We'll talk later about the sampling distribution for b subscript 1 and b subscript 0, but it should hopefully make sense that these distributions exist. Different samples of x and y values will lead to us drawing different lines of best fit. So b1 and b0 are themselves random variables, or realizations of random variables. There's one more thing that we need to consider here. Even if we found the true values beta1 and beta0, we wouldn't expect them to give us perfect predictions every time, any more than finding the true mean and true variance of a normal distribution would allow us to guess what each realization from that normal distribution would be. The fact that we can't draw a straight line through every data point isn't because we don't know precisely which gradient and y-intercept to use, it's because it's literally impossible to find one gradient, one y-intercept that would allow us to draw the straight line through every point. We therefore need to include what we call an error term. We express the true linear relationship as follows. Each value of y is equal to beta1 multiplied by the corresponding value of x plus beta0 plus another value epsilon, which we call the error term. We then call this the regression model for the population. We then also have a regression model for the sample, which replaces beta1 and beta0 with b1 and b0 respectively. Instead of an error term representing the difference between y and beta1 times x plus beta0, we have what we call a residual term, representing the difference between y and b1 times x plus b0. An extremely important point here is that there is a difference between the error term for the true model and the errors we see when applying the regression line we have found via least squares estimation to the data. These residuals are values that we can find and calculate from the model we have created. These are errors in the sense that our model isn't perfectly matching up with the data. They are not, however, the error terms. Those are the errors which exist with regard to the true linear relationship, which we can never find. This means we can never find those actual error terms any more than we can find the true model itself. All we can do is approximate the error terms using residuals. Now we'll talk more about other forms of regression later in the term, but all of them take a similar form to that of simple linear regression. We have a set of inputs x1 through to xp and an output y, all capitalized because these are random variables. We run the inputs through some function and add on an error term, and we get our value of y. Much of what is involved in performing regression is figuring out which form of function we want to use and how we stop the error terms from getting too large and or from behaving in ways difficult to predict. In summary, there are many circumstances in which two random variables, called the independent variable and the dependent variable, have a linear relationship. In such circumstances, the least squares criterion gives us a way to judge how well a line of best fit approximates that relationship, in terms of how close vertically the line comes to each point. The line which minimizes the least squares criterion is known as the regression line, with an equation known as the regression equation. This equation can be used to generate estimates of the dependent variable from the value of the independent variable. Next time on Rick's Maths Corner, we'll take a look at what we can conclude about a situation from the regression line. In particular, we'll consider what the slope and y-intercept values actually represent. We'll also talk about how to tell whether a regression line is too dependent on the location of a small number of points, and how to measure how much of the variance in our dependent variable is explained by the regression line we've drawn. Oyasumi nasai. Guten Tag. In our last video, we took a look at how to take a scatter diagram and draw the best line of best fit possible for a definition of best we call the least squares criterion. We call the line we draw in this way the regression line. We can use this line to take a value from what we call the predictor variable or independent variable and use it to generate an estimated value of what we call the response or dependent variable. In this video, we're going to stick with the idea of what we can do with the regression line and with the regression equation which defines it. Let's talk learning objectives then. In this video, we will explore the meaning of the slope and y-intercept of the regression line. We will consider the limitations of the method in general, and with regard to any given regression line in particular, and we will consider how much of the way the response variable varies is actually being explained by the way the predictor variable varies, by introducing the coefficient of determination. Let's return to our running example of car stopping distances. In our last video, I gave you the regression equation of y hat equals 3.932 times x minus 17.579. Remember, y hat is the estimated value of y we get for a given value of x. What do the values of 3.932 and 17.579 actually represent in this context? In this example, 3.932 is the gradient, the measurement of slope. Each time we add 1 to the value of x, we add 3.932 to the value of y bar. In the context of this example then, the gradient tells us that for every additional 1 unit of speed in miles per hour, we predict an additional 3.932 units of stopping distance in feet. This is how we interpret the gradient in general, in fact. It tells us how much our prediction will increase, or decrease if the gradient is negative, with an increase in 1 unit of the predictor variable. Does the y-intercept have a similar interpretation? The answer is sometimes. By definition, the y-intercept is the value the line takes as it passes through the vertical axis. This is equivalent here to saying the y-intercept is the predicted value for the response variable when the value of the predictor variable is 0. In the car stopping distance example, our prediction for the stopping distance of a car going at 0 miles per hour would therefore be negative 17.579 feet. Now, a prediction of negative 17.579 feet's worth of stopping distance for a stationary car is clearly ridiculous. Now, should this worry us? Not at all. After all, the dataset didn't contain any stationary cars, for reasons I'm sure are obvious. The fact that our model doesn't work for values that lie outside the range of values we were interested in or have looked at, therefore shouldn't be a worry. We just need to remember this point more generally. Now this leads us on to the topic of extrapolation. In the statistical context, extrapolation is the act of using a model to make predictions or estimations using inputs that lie outside the range we use to generate the model. In general, this is a very bad idea, because you're making an assumption that a relationship you've seen in a specific context will hold outside of that context, and you have no evidence that that is true. When you draw a regression line, you should only ever use it to make predictions for predictor variable values which are between the minimum and maximum value of the predictor variable collected in the data. To return to the question of what the y-intercept represents then, it will have a sensible interpretation when the interval of predictor variable values you've used to draw the regression line includes 0. Otherwise it will not. Extrapolation is just one example of the limitations of linear regression. There are other issues we need to consider. We've looked at outliers in a few different contexts already. In the context of linear regression, an outlier is a point that lies far away from the regression line compared to all or most other points. Now, we need to consider what, if anything, we need to do when we see outliers after generating our regression line. And the answer to this, what we do with it, depends on a concept known as influence. So what does influence mean in our context? We call a data point influential if removing it from the dataset would cause the regression line to look very different. Quite literally, the point has a lot of influence on what the regression line looks like. Now, this isn't a desirable property for any point to have, because you do not want your model to be so dependent on where just one value actually is. Outliers very often have high influence. When they do, we need to check them carefully to see if there is any way we can justify removing them from the dataset. Is it perhaps an incorrect measurement? Does the point represent values taken in a very different context to that of all of the others? Now note that an outlier having high influence does not in itself mean we can remove it. We need to believe that it was only included in the first place due to some kind of error. We cannot just remove points because doing so would seem to make our model better. Every model looks brilliant if you just throw away the data points that it is struggling to deal with. Let's go through an example. Suppose we add a 51st point to the car's dataset, representing a car with a speed value of 25 miles per hour and a stopping distance of 1,020 feet. Adding in this new point and recalculating the values for the regression equation shows us that the new line is very different to the old one. If this outlier isn't removed, we're going to be making rather different predictions than we would have done with the outlier gone, and this is a big issue regarding accuracy. In this case, the outlier is clearly influential, and removing it would seem obviously reasonable because a car going at 25 miles per hour is not going to take almost 1/3 of a kilometre to come to a stop. An alternative to removing it, though, would be to check with the original data source to see if an explanation for the strange stopping distance can be found. Perhaps what's happened is that this value has accidentally been expressed in inches rather than feet. There are 12 inches in a foot, so if this were indeed the problem, the true stopping distance would be 85 feet, and that point would no longer be an outlier. Note that the regression line will still change if we add the point 2585 to our previous 50 values, but not to remotely the same extent. The point is now far less influential, as well as not being an outlier. Whether we remove the point or attempt to fix it though, again, we're only allowed to do anything with the outlier because we have good reason to believe it isn't correct. Just the fact that it is an influential outlier in itself is not a justification to remove or change the point. So how do we decide when an outlier is too influential? There's no formal mathematical test to determine when an outlier can be removed, and there's certainly no test for when you should remove it. As I say, that has to be based on your understanding of the data. This is one of those situations in which a statistician must use their best judgment, informed by their prior experiences. That said, we do have a measurement of influence known as Cook's distance, which gives us some idea of which outliers we should be focusing on, and we will be taking a look at that in this week's workshop. A question we've not yet considered is how well our linear regression model fits the data we've used to create it. We know how to use correlation to judge how close the points are to being on a straight line, but we cannot generalize correlation to a case where there are multiple predictor variables. So we won't be able to use it once we move on to multiple linear regression next week. Instead of correlation then, we use the coefficient of determination. I'll define this value in a few minutes, but we have a bit of work to do first in order to set this definition up. We saw in our last video that the regression line is thought of as the best line of best fit because it is the line which minimizes the sum of square values. We can take this idea a little further. The aim of a regression line is to try to use the changes in the predictor variable value to explain the changes in the response variable value. We want to be able to measure how well that explanation is working. Now we can do this by rephrasing our aim. What we are trying to do is to use the variation in x values to explain the variation in y values. Hopefully you'll remember from how all the way back in week 2 I defined variation in terms of the squared distance we expect any individual value of a variable to be from the mean value of that variable. Note that this also relates to squared distances, just like the definition of the regression line. Now take a look at the diagram I've got on screen. Note that I'm using the word deviance rather than difference to bring us in line with common statistical terminology. What we are interested in here is the total deviance between individual values of y subscript I and the mean value of y subscript I. This is expressed as y subscript I minus y subscript I bar. Now this deviance can be divided into two parts, yi hat minus y bar and yi minus yi hat. The first of these two parts represents the deviance we have successfully explained using the regression line. The second, which as we saw in the last video is known as the residual, represents the deviance we have failed to explain. Now I won't go through this equation, you can give it a go for yourselves as an exercise if you'd like, but the useful property for us here is that if you square the value of explained deviance, square the value of unexplained deviance, and add them together, you get the squared value of the overall deviance. We call the sum of squared values of the deviance explained by our regression the regression sum of squares, or SSR. We call the sum of squared values of the unexplained deviance the error sum of squares, or SSE. These then sum together to give us the total sum of squares, or SST. Now there are two important things to note about the SST. The first is that it is calculated just using the y values. It has nothing to do with the line of best fit at all. Any line of best fit we draw, no matter how good or bad, will give us a sum of squares for how much that deviance is explained and a sum of squares for how much deviance isn't explained, which sums to the total sum of squares. What makes the regression line special is it minimizes the error sum of squares and therefore maximizes the regression sum of squares. The second important fact about the SST is that if you divide it by n-1, you get the sample variance of the y values. So the SSR divided by n-1 plus the SSE divided by n-1 gives us the sample variance of y. It is for this reason that we can talk about how much of the sample variance the regression line is explaining. Before we move on, I need to make an important public service announcement. Exercise caution with your acronyms. Some people call the error sum of squares the residual sum of squares, which they shorten to RSS. This means RSS is the same thing as SST in our notation, not the same thing as SSR. This is unnecessarily confusing and extremely annoying, and this means you always need to be sure you understand which names are being given to which terms when looking at sums of square values. Right, back to the maths. How does any of this help us? The basic idea here is that the better the regression line fits the data, the smaller SSE will be and the larger SSR will be. Remember, these values sum to give SST, and SST is a value we get from the data itself, completely independent of what line we've drawn. The smallest the SSE can be is 0, which means the points all lie on a straight line anyway. The smallest SSR can be is also 0, and that represents drawing a horizontal line of best fit. Such a line would explain none of the variance of y in terms of the variance of x, because the line will give the same estimate of y no matter what value of x is being used. What we're going to do now then is define a measurement for how well a regression line is working, which takes its maximum value when the SSE is 0 and which takes its minimum value when the SSR is 0. This is done using the coefficient of determination. We denote this by capital R squared, and often we just call it capital R squared rather than the coefficient of determination. Capital R squared is defined as being the value of SSR divided by the value of SST. When SSR is 0, R squared is also 0, and that can only happen when we've drawn a horizontal line of best fit. When SSR and SST are equal, R squared is equal to 1, and this can only happen when SSE is 0, meaning all points are lying on the line. More generally, the closer R squared is to 1, the better the regression line is doing in explaining the variation in the response variable. Now, as an extremely rough rule of thumb, you would want R squared to be at least 0.7 before you claim the regression model is a good explanation for the underlying relationship between your variables. So why do we use a notation capital R squared? We saw in our first video this week how the correlation we most commonly calculate to express the strength of a linear relationship between two random variables is the Bravais correlation coefficient, denoted lowercase r. In fact, for simple linear regression, if you take the correlation value little r and square it, you will always get the coefficient of determination, capital R squared. This only works for simple linear regression though. Indeed, once we have more than one predictor variable, we will not be able to calculate a correlation at all, but we will still be able to calculate the coefficient of determination. That's why we need it. Okay, time to sum up, I reckon. When we draw a regression line, we can always interpret the slope as being how much of a change in the response variable we expect following an increase of 1 unit in the predictor variable. Outliers can have great influence on a regression line, making the line look quite different to how it would look like were those values removed. So each of those points should be carefully considered to see if we can justify their removal. Finally, we can calculate the coefficient of determination to judge how well a regression line fits the data. So now we have a method for checking how well our regression line expresses a true underlying relationship between two random variables. All of this, though, will only be of any use at all if it's sensible to be trying to estimate a linear relationship between our variables in the first place. In our next video, we'll be considering what assumptions need to hold in order for linear regression to be a sensible approach to take when modelling data. That's it for now though. Auf Wiedersehen. Hola! Welcome to another Week 6 video and another look at linear regression. We really only have one more topic left to consider this week, but it's quite a subtle and important one, so we're going to be looking at it over 2 videos. Let's start with a quick reminder of what we've learned about linear regression so far. Simple linear regression is the process by which we fit what we call a regression line to paired data points, x1, y1 through to xn, yn, using the least squares criterion. We do this in order to estimate values of the response variable y from the predictor variable x. We make the assumption that there is some underlying true linear relationship between x and y, expressed through the equation little y equals beta 1 times little x plus beta naught plus epsilon, where epsilon is known as the error term. Although we assume beta 1 and beta naught exist, we can never actually find them. We can only estimate them. We do this by using the regression equation to generate b1 and b0, our estimates for beta 1 and beta naught respectively. We use those values to generate y hat. These are our estimates for the y values. Lastly, we can use the coefficient of determination r squared to measure how much of the variance in the response variable y is explained by varying the predictor variable x. Right, that's us up to date. What's next? Generating the regression line is really only the start of our process. We want to be able to make estimations or predictions from the line we've drawn. We also want to be able to say how accurate we expect the values we're generating from that line to be, and to have options for improving that accuracy if possible. Our learning objectives for the video then. We're going to go through the 4 assumptions we need or want to make about the true linear model in order to rely on our approximation of that model. Then in the final video for this week, we'll consider how we can check if those assumptions hold, and if not, whether or not there is anything we can do about that fact. Our focus for this video is what we call the simple linear regression assumptions, or SLR assumptions. In fact though, each of these assumptions applies to multiple linear regression as well, as we shall see next week. All 4 of our assumptions relate to the error terms. As a reminder, the error term is the difference between yi and beta 1 times xi plus beta naught. These terms have to exist even for the true model because there is no line we can draw that will pass through every point. But what are these error terms? How do they behave? Well, since they can change from data point to data point, and we don't and can't know how they'll change from data point to data point, we can think of each epsilon value as being a random variable. All 4 of the simple linear regression assumptions involve the behaviour of these random variables. To make full use of this idea, we're going to assume that we have a known value of xi, and we're interested in the corresponding value of capital Yi, a random variable we have not yet seen the value of. Now this clearly isn't true for the data we are using to create our regression line, but we can imagine that going forward, we might have values for little x for which we do not have the corresponding values of little y, and hence use capital Y instead. That's one of the reasons we want to create a linear regression model in the first place, to make predictions about missing y's from present x's. Under this assumption, we can say epsilon I is equal to capital Yi minus beta naught minus beta 1 multiplied by little xi. Now, if that doesn't make complete sense straight away, I wouldn't worry. The important idea here is the assumptions we want to be able to make about the distribution of the random variables epsilon 1 through to epsilon n. It's very important to note here that we are talking about assumptions for the error terms themselves and not assumptions for the residuals, which are our estimates for the error terms. As I've talked about before, we can never know the actual values of the error terms, only the residuals. We're going to take a look next video at how we can check the following assumptions about the error terms without actually knowing what those error terms are. So, the 4 assumptions we make are as follows. We assume every error term has an expected value of 0, no matter what the corresponding value of little xi. This means we expect the model to have an average error of 0. Sometimes we'll get an overestimate from our model, sometimes we'll get an underestimate from our model, but we expect these to average out over the long term. We assume that the variance is equal for every error term. In other words, all error terms have the same variance no matter the corresponding value of xi. This is to avoid situations in which, say, larger values of xi result in larger variances for epsilon I. We do not want our model to be less reliable for certain values of x than it is for others. We assume each of the epsilon I values are independent of all the other values. We want to be able to say that learning something about one of the values of epsilon I tells us nothing about any of the other values. A situation in which learning about, say, epsilon 1 gives us information about epsilon 2 suggests there exists an underlying pattern in the errors, which in turn suggests there's something that we haven't taken into account when we drew our regression line. All 3 of these assumptions are necessary for linear regression to work. Without them, we cannot say that we can rely on the estimates or predictions we get from the line. Now there is another assumption, a 4th assumption, which isn't necessary for linear regression to function, but which is necessary in order to perform all sorts of useful processes, such as calculating confidence intervals for the estimates we make. This 4th assumption is that each epsilon I is a realization from a normal distribution. From the first 3 assumptions, that normal distribution therefore must have a mean of 0 and a variance of sigma squared, and the realizations from this distribution must be independent of each other. We will now combine these 4 assumptions and our equation for epsilon I with what we learned about conditional probability distributions back in week 3. And we'll do this to see how we can express the process of getting estimates or predictions from regression lines in terms of probability theory. Assumption 1 tells us that for a value of little xi, the expected value of capital Yi is beta 1 times little xi plus beta 0. That means that in conditional probability terms, we have the expected value of capital Yi given capital Xi equals little xi is equal to beta 1 times little xi plus beta 0. This means that when we know a value of xi, we have an expected value for capital Yi, or at least we would have that if we knew the beta values. Instead, we have an approximation for it. Assumption 2 tells us that for a value of little xi, the variance of capital Yi is always sigma squared. In conditional probability terms, we have that the variance of capital Yi given capital Xi equals little xi is sigma squared. Assumption 3 tells us that capital Yi and capital Yj are independent when I and j are different numbers. Finally, assumption 4 tells us capital Yi is normally distributed. This comes from the fact we've seen before that the linear transformation of any normal random variable is also normally distributed. These first 2 assumptions give us what the expected value and variance of yi given xi must be, and we therefore have that yi given capital Xi equals little xi is normally distributed with mean beta 1 times little xi plus beta 0 and variance sigma squared. Now I realise that is an awful lot of notation and equations to throw at you. Let's take a look at a graphical representation of the situation. In this diagram, the red line represents the true linear relationship between capital X and capital Y. Now we can't find this in practice, as we've talked about, but we can still represent it graphically for the purposes of this explanation. We also have 3 data points, little x1, little y1, little x2, little y2, and little x3, little y3 in blue. The 3 values of the predictor variable, little x1, little x2, and little x3, give us 3 values of beta 1 times little xi plus beta 0. And these are the yellow points on the line. Note that I'm not referring to these points as involving y hat 1, y hat 2, and y hat 3, because y hat is the notation we use in the context of the regression line we draw, not the true linear relationship that is being expressed here. The differences between the yellow points and the blue points are marked out here using dashed green lines. The lengths of these dashed lines represent the error terms epsilon 1, epsilon 2, and epsilon 3. Each of these epsilon values is a realization from a normal distribution, with the probability density functions of those normal distributions drawn here in light blue. The variance of each of these normal distributions is the same, sigma squared, but their expected values are different. For each yellow point, the expected value of the normal distribution is the y value at that point. Now, it's these values that explain the difference between the yellow points and the blue points. What would happen if we collected a new predictor variable value, little x4, that happened to be equal to little x1? Well, our expected value for capital Y4 would be the same as it was for capital Y1. The actual value of capital Y4 would almost certainly be different though, because while the corresponding value of epsilon 4 would be a realization from the same normal distribution as was epsilon 1, we wouldn't expect those 2 realizations to be identical. Indeed, technically the probability of epsilon 4 and epsilon 1 being identical is 0. Let's quickly run through an example of what data generated by these assumptions looks like. Let's consider a situation in which the true linear relationship between x and y takes the form capital Yi equals 2 times little xi minus 1 plus epsilon I, where each epsilon I is independently drawn from a normal distribution with expected value 0 and standard deviation sigma squared. I'll generate 100 values for x from the uniform distribution u0 to 10 and 100 epsilon values from n0 sigma squared. Doing this will allow me to generate 100 values of y. Firstly, I'll set sigma squared equal to 0.01. We can see that this model generates points that are extremely close to lying on a straight line. If I now increase the value of sigma squared to 1, whilst using the same x values, we get a rather different picture. Now, both situations use the same values of little xi, beta 1 and beta 0. Because the second dataset was simulated using a larger value of sigma squared though, there's a greater variation of the points around the line beta 1 times little x plus beta 0. One of the clever things R does for us, when it draws a regression line, is estimate the value of sigma squared for the data. And we'll talk more about that another time. So those are the assumptions we need, or at least want, in order for us to make full use of a simple linear regression line. The next question is how we check whether those assumptions are actually holding for the regression line we have drawn, which will be the focus of our final video for week 6. Adios. Sure. We're into our final video of week 6, and we're going to be continuing our exploration of simple linear regression. In our last video, we took a look at the assumptions about the error terms we make when performing linear regression. We'll start here with a reminder of what those assumptions are. As before, we'll talk about all of this in the context of the simple linear regression model we've been looking at this week. But the assumptions we define here all apply to all linear regression models, not just the simple form. Firstly, a reminder of what the error term is. This is the difference between the actual value of y and what the true linear model predicts as being the value for y, for a given value of the predictor variable x. We are assuming here that epsilon and y are both random variables, whereas x is not. This is because we usually think about these models in the context of knowing the value of x and wanting to know what we can say about an unknown corresponding value of y. We commonly use a subscript I here to represent the difference between these two values for the ith data point. We went through 4 assumptions last video. Firstly, the expected value of each epsilon I should be 0. Second, the variance of each epsilon I should be the same, no matter which point I we are looking at. Third, epsilon I and epsilon j should be independent whenever I and j are different numbers. These 3 assumptions are necessary for linear regression to work at all. There is a 4th assumption, which isn't strictly speaking necessary, but which is very helpful for many reasons. This assumption is that the epsilon I values are normally distributed. In combination with the other 3 assumptions, this assumption gives us that each epsilon I is identically and independently normally distributed, with a mean value of 0 and a variance of sigma squared. Okay, that's us all caught up. In this video, our learning objectives are to answer 2 questions. Number 1, how can we check whether these 4 assumptions hold? And number 2, what do we do if it turns out they don't? I'm going to answer both questions as we go along for each of the 4 assumptions. Before we can get anywhere with these questions, though, we have what might seem like a huge problem to deal with. As I mentioned last video, we can never actually know the values of each epsilon I. We cannot know what they actually are. Instead, we're going to have to check the behaviour of the residuals. As we've seen before, the residual of point xi, yi is denoted ei, where ei is equal to yi minus y hat I. These are the differences between the actual values of yi and what the regression line we have calculated gives us our expected values of yi. Each ei is not the same as the corresponding error epsilon I, they are approximations of these errors. In order to check whether our errors are behaving according to our assumptions then, we check for equivalent behaviour in the residual values. We can do this by drawing a residual plot. The residual plot is a scatter diagram which plots the residual values ei against the corresponding values of yi hat, or, less often, against xi. As an example, this is the residual plot for the cars data in R. Each value on the horizontal axis is an estimated stopping distance in feet. Each value of the vertical axis is the difference between the estimated stopping distance and the actual stopping distance, again in feet. We'll consider how to interpret this plot with regard to our assumptions. First up, linearity. We need our assumption of a linear model to be plausible in order to believe that the expected value of all residuals is 0. If the linear model isn't plausible, we will see that the residuals have different expected values across the range of x, sometimes positive, sometimes negative, certainly not always 0 as we require. Whether we have linearity can generally be detected directly from drawing the regression line on the scatter diagram, but we can also do this through the use of a residual plot. Let's look at an example of this in R. The Indometh dataset gives us the concentration of the anti-inflammatory drug indomethacin in micrograms per milliliter in the bloodstream of people injected with the drug. This concentration is the response variable, with the predictor variable being time in hours since the injection happened. If I show you the data points along with the regression line, you can probably already see the issue. The data has a curved relationship which the regression line cannot capture. As a result, the value of r squared here is just 0.504. If we look instead at the residual plot, we see the same issue. If the linear assumption were holding, we'd expect to see as many residuals above the horizontal line as below it, with no obvious pattern as to which are above and which are below. However, there is a clear pattern here. Residuals for small and large fitted values are generally positive. Residuals for mid-range fitted values are generally negative. This means the regression line is underestimating concentration levels for small and large times and overestimating them for the times in between. So how can we fix this? A common approach is to apply a transformation to the predictor variable. There are many such transformations. We can change x to x squared, or to the square root of x, or to 1 over x, and so on. The transformation we'll use here is a very commonly used one. We're going to apply the natural logarithm function, ln of x, or if you're working in R, log of x. If we perform this transformation, the new regression line for the new scatter diagram looks much nicer. Further, the r squared value is much improved, now being 0.820. We see a similar improvement in the residual plot. The problem most certainly hasn't completely gone away, but it has been much reduced. So we've improved things, both in terms of how well the regression line fits the data, and how well the underlying linear assumption appears to hold. Now, it is no coincidence both of these have improved at the same time. R squared is measuring how much of the variance in the response variable can be explained by a linear model. And what we've been doing is checking to see if a linear model appears reasonable. It shouldn't be a surprise that improving the reasonability of the linear model also improves the fit of that linear model. One more thing to consider before we move on to the next assumption is why we're allowed to apply a transformation in this way. We're currently in the business of considering how well a linear relationship works. Now, the log function isn't a linear function at all, so isn't it somehow cheating to apply a nonlinear transformation? Well, this gets us to a common misconception about linear relationships. In fact, the relationship only needs to be linear in the parameters. What I mean by that is, so long as we get from our predictor value to our estimated response value by multiplying by b1 and adding b0, it doesn't matter what transformations we've run either x or y through first. What we're not allowed to do is apply a nonlinear transformation to the overall value of b1 times x plus b0. On to our second assumption, which is constant variance. We want the variance in our errors to remain the same across the range of predictor variable values. This too we can check by looking at the residual plot. In order to check the assumption of linearity, we check the residual plot for a pattern. To check the assumption of constant variance, we're looking for a different sort of pattern. If we don't have constant variance, we'll see the spread of residuals change across the residual plot. Maybe they'll be larger on the left than the right, or vice versa. We call such patterns left opening fans and right opening fans respectively, or sometimes left opening and right opening trumpets. On screen now, I have an example of a right opening fan. We can see that the higher the fitted value, the greater the variance of the residuals. In other words, the larger the value of the predictor variable, the more uncertainty we have in what the residual will be. More rarely, we might see a larger spread in the middle than at both ends, or vice versa. In any of these cases, the assumption of constant variance has been violated. Now, this will make all sorts of approaches, such as hypothesis testing and the calculation of confidence intervals, very difficult to apply, as both rely on having an estimate of sigma squared. The mathematical term for constant variance is homoscedasticity, which is almost as hard to say as it is to spell. The word roughly translates as same in comparison. Any of the patterns I just described tells us that we have instead heteroscedasticity. Other ways to detect heteroscedasticity are the Goldfield-Quant and Brush-Pagan tests. I'm not going to go into those, but they replace the visual check of the residual plot with a hypothesis test with an attached p-value. So what do we do when heteroscedasticity is present? The simplest approach here is once again to attempt to minimize the problems through a transformation, this time of the response variable. Transformations like the natural logarithm, square root, or cube root are all often helpful in reducing heteroscedasticity. Next up is our third assumption, that the error terms are independent. That means that we are assuming learning something about the value of one error value, say by learning the residual value that approximates it, gives us no information about any other error value. When this assumption is violated, we refer to the residuals as displaying autocorrelation. Autocorrelation, as the term might suggest, refers to the correlation a sequence of numbers has with itself. Now that might sound odd, but defining and finding it are comparatively painless. To find the autocorrelations of residuals e to n, we create a series of pairs, e2, e1, e3, e2, and so on all the way up to en minus 1. We then find the Bravais correlation coefficient for those pairs. Now, autocorrelation in residuals is bad, because even quite a small amount of autocorrelation means learning the value of one residual is giving you some information about the next residual, and that violates the assumption of independence. Now, an alternative to calculating the autocorrelation is just to take a look at the residual plot again. If nearby residuals take similar values compared to the spread of residuals overall, you've got autocorrelation. That said, the pairing method I just discussed is generally easier to interpret. On screen is an example of residuals which display autocorrelation. In this case, each residual value is generally larger than the residual value that precedes it, corresponding to a positive correlation, positive autocorrelation. On the left is the plot of the predictor variable time against the residuals. It is difficult to make out the autocorrelation in the residual plot on the left, but once we pair the residuals and put them in the plot on the right, we can see there is a definite positive correlation in that plot, which means a definite positive autocorrelation for the errors, which violates our assumption of independence. In comparison, here is an example where autocorrelation is absent. So why does autocorrelation occur? We often see it in situations where we are considering time series data, because often we don't expect values to change as much over the short term as they will over the long term, meaning residuals close to each other are likely to look quite similar. Now that isn't the only way that autocorrelation can occur, but it gives us a good sense of where the problem tends to lie. There is some variable we haven't considered which is ordering our data in such a way that autoregression is happening. So what do we do in response? Sometimes the problem might just be that someone has previously ordered the data in ascending or descending order by mistake. If that's the case, we can just randomly order the data and we're sorted. If there's an actual relevant variable that's missing though, we either need to figure out what that variable is and account to it, usually by adding it into the model, which we'll talk more about next week, or we need to abandon linear regression as an approach and try a more complicated model which can take autoregression into account. You may see some of those next term. Our final assumption is that the errors are normally distributed. Now this is actually quite simple to check because we already know how to check for normality. We can use a QQ plot or we can use the Shapiro-Wilk test. We just apply one or both of these to our residuals. If doing so reveals non-normal behavior, we can once again attempt to solve the problem by applying a transform to the response variable. The natural log of y, the square root of y, and 1 over y are all good transformations to attempt. Collecting more data can also solve this problem. It might be a lack of data values is hiding the fact that we're actually seeing normal behavior. This is something we will look at in this week's workshop. Okay, we've reached the end of this week's theory. In summary, there are 3 assumptions we require be true in order to make use of simple linear regression in a given case, and a 4th assumption that we strongly desire to be true. Each of these assumptions has 1 or more associated methods through which they can be checked, and we have possible solutions we can apply in situations where those checks have identified a problem. So, that's it for week 6, and for the first half of our exploration of linear regression. Next week, we'll be looking at how to assess the accuracy of the values of B0 and B1 we've calculated. We'll look at how to generate a linear regression model for a categorical predictor variable, and perhaps most excitingly of all, we're going to learn how we can generate a regression model using more than one predictive variable at once. До свидания.